Okay, class, welcome back. Today is lecture 14. Today we're talking about two things, sort of combining two lectures into one, rational expressions and exponent properties. So they're not too related to each other, but we got to sort of squeeze in exponent properties somewhere. And so today's the day that we do that. But first we're going to talk about rational expressions. So what are these things? A rational expression. Well, rational means fraction. So it's going to be a fraction. It's the quotient, another fancy way to say fraction, of two polynomials. Remember, those are powers of x added together with numbers multiplied to them. So let's just jump into seeing some examples. So all I need is one polynomial divided by another polynomial. So that counts as a rational expression. Here's another one. You can make lots of them. Various powers of x, things like this. These are rational expressions. Remember, polynomials can be just numbers. In fact, this just counts as an x to the 0. So even something like this is a rational expression. Okay, so what we want to do is learn how to manipulate these and combine them and simplify, sort of how we do with lots of other things. So first, let's see how to multiply two of these guys together. So we're going to simplify the following, and it's going to be two rational expressions multiplied together. So I got x plus 4 over x squared minus 9 times another one, x minus 3 over x minus 5. So how do I multiply these two things? Well, they are fractions, and so you just multiply across the top and across the bottom. And so what we're going to do is make our life easy. So the top is x plus 4, and that whole thing is being multiplied by the whole x minus 3. So you got to have these parentheses here. If you just stick them next to each other without parentheses, you're going to get all mixed up. So that's what it actually looks like. And then same down here. So multiplying fractions, you just multiply across the top, across the bottom. Make sure you have parentheses so it's clear what's being multiplied to what. Okay, but now what we can do is we can simplify. So what we're going to do is we're going to factor as much as we can. And that's going to let us simplify a lot. So on the top, everything is already factored as much as you can factor it. We don't want to stick it together because that'll make it look less nice, actually. We like our polynomials to be factored. But what about on the bottom here? We can actually do something. So typically, you can have some sort of scratch work on the side where you try to factor things. And what we can realize is x squared minus 9 is actually a difference of squares. So it factors into x minus 3, x plus 3. And then all we're doing is we're going to replace that with this. So x squared minus 9 becomes x minus 3, x plus 3. And then the x minus 5 I have not changed. Now we can simplify further because what we need to realize is that multiplication has this fun property called commutativity. So if I multiply two numbers together, it's the same as multiplying them in reverse. And you can do the same thing with polynomials. So this x minus 3, I can put in front of the x plus 4, and then I can sort of see something happening, which is that I have an x minus 3 divided by an x minus 3. So off to the side, we can go and realize that if you divide the same exact thing by itself, that's always 1. Anything divided by itself, it doesn't matter what it is 1. And so that just becomes 1 And 1 times anything keeps the thing the same, so we can just not write it anymore. That's why you often don't write ones that are multiplied to things. And then it just becomes this. Now, the shortcut is people will often do this. They'll look at this guy and they'll say, aha, I see an x minus 3 on the top. I see an x minus 3 on the bottom, so they cancel, and they'll just call it canceling. And that's fine too, as long as you understand, but people often get mixed up when they try to cancel things that don't make sense to cancel. So at this point, we are done. So let me just show you what people do that's bad. So sometimes they'll just see like, oh, I see an x here. I see an x here. So I'll somehow, I'll just cancel that and that because they're the same. But that logic doesn't follow here. And so that's the problem with canceling too much like that, or thinking about it in that way. Instead, what's happening is when you divide the same thing over itself, you can cancel them. But x is not being divided by x. That would look like this, x divided by x. That would be 1, sure. But x plus 4 over x plus 3 is not the same as x over x, because that's not how fractions work. This is not saying x over x plus 4 over 3, right? That's not how fractions work. You can't just split them up like that. When you add them, you have to do common denominators. So never try to cancel like that. You can only cancel multiplication over multiplication. So if you see a term being multiplied on the top and the bottom, then you can cancel it. Like these x minus 3s are both being multiplied on the top and the bottom to the rest of it. So that's why they can cancel. Okay, so that is going to come in handy quite a lot. So let's try not to make that mistake. All right, but next example. So that's how you multiply two rational expressions. What about dividing? Well, dividing is pretty much the same as multiplying, but a little bit different. So let's do another one, which is going to also be slightly more complicated. So instead of multiplication, we're dividing. And the trick is to know that division is the same as multiplication, but upside down. So that's what we're going to take advantage of. So here we're going to use this property. So if you divide by a fraction, something like this, a divided by c over d, that's the same as multiplying by d over c. And people often write it like this, a divided by c over d, and then they change it to multiplication by flipping it over like that as well. So this is the same property written 2 different ways. Okay, so that's what we're going to use. So this guy is going to become 3x squared plus 4x plus 1 over 3x squared minus 5x minus 2. So see, I'm not dividing that, so that's going to stay exactly the same. I'm dividing by this next thing, so that's the thing that gets flipped over. So the next thing gets flipped over, and this guy goes on top. And now it's exactly, whoops, I flipped it over, so that the x squared is on the bottom. X squared minus 2x minus 1 is on the bottom. So now it's exactly like the previous problem, and it's multiplication again. So all I have to do is multiply across. So it's this thing times this thing, and then this thing times this thing on the bottom. But what you can do is you can actually factor before you stick them together if you want. If you want, it doesn't matter. So I put a question mark. You can put them together first and then factor, or you can factor and then put them together. So what I'm going to do is off to the side somewhere, maybe I'll do it down here. I will factor these things as best I can. So for example, 3x squared plus 4x plus 1, I can do my little box here. So it's got to multiply to 3 and add to 4. And then let's see, what does that? How about just 3 and 1? So then this is 3x squared plus 3x plus x plus 1. Then I group things up. X was just left there, and a 1 is left here. Nothing comes out of x plus 1. Nothing needs to. So then I take out my x plus 1, and what's left is 3x and a 1. So that's going to be what goes there, x plus 1 times 3x plus 1. So lots of factoring, unfortunately. Okay, but good thing we got really good at it last time. So what about this one? Well, this guy, I can do the same thing, -6, -5. So -3 and -2 work there. So this becomes -3x minus 2x minus 2. Take out a 3 and an x. Get just an x and a -1 left. Take out a -1 here. And we get a -2. And then you also get an x minus 1. Take out those x minus 1s. And you're left with 3x minus 2. So that's going to factor. So that's what this bottom one becomes. Okay, and now we'll factor. Let's see, any more scratch room area. So now I need to factor this -5x squared plus 25x minus 30. For this one, I'm actually going to take out a -5 first, and it'll make my life easier. So then I can now just factor the x squared minus 5x plus 6 by realizing that -3 and -2 multiply to be 6 and add to be -5. Okay, so that's going to go here now. I've replaced that one. And let's see. Sorry, I have to check something. I think I messed up somewhere. To check real quick. I think I messed this one up here. 3x squared minus 5x minus 2. Let me just check it real quick because I'm worried. Yep, I did mess up. So I took out a -3x there, in fact. Oh, wait, no, I didn't. Sorry. What's going on? 3x minus 2. X minus 1. Sorry, I'm going to pause it real quick so I can stop messing up. Okay, now I see it. -3 times -2. I was trying to go too quick. That does not multiply to be -6. That multiplies to be +6. So in fact, I need a -6 and a +1 because that will work, and also add to -5. So tried to be a little bit too quick. Let's fix that up. So this is going to be a -6x plus an x minus 2. Take out a 3x, and I have x minus 2. And over here, I don't have to take out anything. And now I take out an x minus 2 from both of these to get 3x, and a 1 is left there. Okay, so that's what's going to go there on the bottom. So let's fix that. X minus 2 times 3x plus 1. And okay, last one. Now I just have to factor this x squared minus 2x minus 1. That's going to be x. Let's see, that would just be. What am I doing? Oh, wait, it was a 3. Haha. That's why, man, so many screw ups right now. Yeah, this should be a 3. I don't know why I wrote a 1 there. Sorry about that. Oh, I wrote a, yeah. This should be a 3. That should be a 3. Sorry for the typos. Okay, so now x squared minus 2x minus 3 factors into x minus 3 times x plus 1. Okay, now we're good. So now I can multiply by just sticking everything on the top and everything on the bottom being multiplied together. And because everything is being multiplied together, I can do nice cancellations whenever I see something that's the same on the top and the bottom. That's only because everything is being multiplied together. So each factor that's the same can be canceled if you see it on the top and bottom. And here we see a lot. So we see an x minus 2 and x minus 2. an x plus 1, an x plus 1, an x minus 3, an x minus 3, and a 3x plus 1 and a 3x plus 1. So what's left? Well, those all just become 1s. So 1 times 1, but then there's still this negative 5 times 1 times 1. So this ends up just simplifying to negative 5. Okay, so that's how these work. Up next is addition. So what about when I want to add rational expressions? Well, just like adding fractions, I need a common denominator. So that's going to be the same. So I have one rational expression added to another, and to put them together, we need a common denominator. Now, how do we get a common denominator? Well, first, before we think about that, we are going to try to factor as much as possible. So x minus 4 is already factored, but x squared plus 4x plus 3, we can factor as x plus 3, x plus 1. So that's becoming that. And then x minus 1 is already factored as much as possible, but x squared minus 9 is a difference of squares. So I can do x minus 3x plus 3. So that's becoming that. Okay, so now it's a little bit easier to get a common denominator. So what does getting a common denominator mean? It means that the denominators need to be exactly the same. They need to be the same. And they're not right now. So how can I make them be the same? Well, you can think about it as if they were numbers on the bottom. So it's sort of like I have a 5 times a 2 and a 3 times a 5. So I have 2 of the same. I already have x plus 3s on both. So those are the same. But this guy, this one needs an x plus 1, and this one doesn't have the x minus 3. So how do I just declare them down there? Well, I can't do that. I can only multiply by 1 without changing things. So what I need to do is multiply by what I need over itself. So this first guy needs an x minus 3 on the bottom. So I'm going to just multiply it down there, but I'm going to multiply it over itself. So that technically speaking, I'm multiplying by 1, which does not change anything. And the whole point is you can't just change it. It's got to be exactly the same. And then this other fraction, he needs, in order to match the other one, he needs an x plus 1. So I'm going to multiply this one by x plus 1 over x plus 1. And now we're sort of doing what we did before, but in 2 different spots. So how do you multiply rational expressions? You just go across. So on top over here, I get x minus 4, x minus 3 over, now this one has all 3. And the other one will have the same all 3 on the bottom. They might be in different orders, but they're the same because they're multiplied to each other. And you can reorganize them in the same order as well. And then on top is this. So now that they have the same denominator, I can actually add them together and put them under that same exact denominator. And then on top, I just have them added together. Now at this point, the problem is that we have this addition, which is sort of bad. It's preventing us from factoring. So what we actually need to do, so just because these are individually factored, doesn't mean that the top is actually factored. So what we need to do is we need to actually multiply these out and then stick them all together after. So that's the last step. These problems are kind of long. That's okay. Okay, so if I multiply x minus 4 times x minus 3, I get x squared minus 4x minus 3x plus 12 plus, and now I have this other stuff, x squared minus x plus x minus 1. So I'm just going to simplify the top. The bottom is already simplified because it's already factored out nicely. but the top is not factored out. So now I can put things together. So I have x squared plus x squared is 2x squared minus 7x minus x plus x, that cancels to 0. And then I have 12 minus 1 is 11. And this actually is not going to factor. Not going to factor. So we're just going to leave it like this and say we're done. If it did factor more, then that's how you would continue simplifying. But that one doesn't factor. Okay, so that's how you add. Get a common denominator, then stick them together, and then simplify as much as possible. Okay, and now what's the last operation? Subtraction. So subtraction will work just like addition, but there will be a negative. And these just take practice to work with. Okay, so here's what we can do. So instead of adding these two rational expressions, we're going to subtract them. And it works the same as the previous one. So first we're going to factor individually as much as possible. So let's see, 3x minus 1 is already factored. X squared plus 2x minus 3 will be factored as x plus 3, x minus 1. And then I still have this subtraction. I'm not going to do anything with it yet. It's just there. X plus 4 over, and this guy factors x minus 3, x plus 3. Okay, so what people like to do is they don't like to make a whole new step to get common denominators, so they just sort of stick them on the end here, and they look on the other side and see what they need. So this guy has an x minus 1 that this one doesn't have, so I need to multiply by x minus 1 over x minus 1. And then the other guy has an x minus 3 that this one doesn't have. So let's see if I can squeeze it in here. I'm going to multiply x minus 3 over x minus 3. And then all in one step, I'm going to realize that now both of them have the same denominator, because that was the whole point. They have these three things multiplied together as their denominator, so I can put them together. And then on the top up on the left, I have x minus 3 times 3x minus 1. And on the top on the other side, I have x plus 4 times x minus 1. And now the only difference is from last time is that I have a minus in between these two instead of a plus. And that's going to have to distribute at some point. But we're still going to do the same thing we did last time, which is we're going to multiply these together to simplify a little bit, because if it was all multiplication, that would be fine. That'd be nice because everything's factored and multiplied together, and then we could look for canceling. But because we have this subtraction between the two, it sort of doesn't help that they're factored individually. So we're going to put them together. Okay, x times 3x gives me 3x squared. X times minus 1 is minus x, minus 9x, and plus 3. Then I have this subtraction. And now this is the key part. This subtraction is being applied to this whole thing here. So I got to keep it on the outside. I can't forget this parentheses because the subtraction is going to be applied to everything inside of the parentheses. So x times x is x squared, 4x minus x, and minus 4. So that's the key difference, is this subtraction is on the outside of everything that you have there on the top. And now we can simplify. We'll do it a couple steps at a time. So on the bottom is really not changing at all. Up top, I have 3x squared. This becomes minus 10x plus 3 minus x squared plus 3x and minus 4. And now I'm going to distribute this negative through so that I can combine everything together. Okay, so you can skip a lot of these steps once you sort of see it with lots of practice. Okay, so 3x squared minus 10x plus 3 minus x squared minus 3x plus 4, because I've distributed that negative. Now I can finally combine like terms. So 3x squared minus x squared is 2x squared, negative 10x minus 3x is negative 13x, and 3 plus 4 is 7. So That is the end, unless you can factor the top. But I don't know if this one factors out nicely. It might actually. 14. No, it does not. Okay. So that's going to be it for us there. So I could do another example. Do I want to do one more? Sure. If you got it already, then you can sort of skip ahead on this example and jump to the next section, which is when I talk about exponent rules. But I'll do one more example for those of you that want to see one more example. And I'll do one more subtraction example. Okay, so but I'm going to do it a little bit faster. So let's see, the bottom needs to be factored into x plus 3, x minus 2. Here I can take out a -5. X minus 1 is left. Sorry, x plus 1 is left because I took out the -5. Then here I have an x plus 1, and here I have an x minus 2. So this time, the only thing that's missing is this x plus 3 from the right side. The left side already has both in common now, so I don't have to do anything to the left side, actually. So now I just have this. So on the top, I will combine these two with a subtraction in the middle, and on the bottom now I just have the common denominator. X plus 3, x minus 2 is what they have in common, is what I made them have in common. And now on the top, so I could do what I did before, but I could actually be sneaky. This one's a little bit easier. If I see it just right, there's an x plus 1 and an x plus 1 here. And so I can factor it out without multiplying everything out and sticking it together. It'll work the same. But if I factor that x plus 1 out, what's left is this -5 and minus this x plus 3. And so it looks a bit strange. But then I can continue simplifying. So this is nice because I do have the multiplication of two things on the top and on the bottom, so things are nice and factored. And so if they were the same, I would be able to cancel, but they're not. So I have to do this thing though, minus x minus 3. So -5 minus x minus 3. And so that's going to end up being, well, I'm going to put the numbers together, -8 minus x and x plus 3 over x minus 2. So see, none of these factors are the same, so we're not going to cancel. This is it. Okay, so I mean, there's only so many examples I can do. They're all very similar, but they sort of just take lots of practice. So make sure you practice on the lecture problems a lot. Now I'm going to move on to the second half of this video. It should be much shorter. I'm just going to talk about some exponent rules that you've probably seen before, but I want to remind you of them just for future use in pre-calc or something. Very important to know where these things come from. So A is going to be some number. Then let's think about some rules. So what does a to the n power mean? So the exponent is the number above the a. That just means to multiply a together n times. So whatever n is, that's how many times you do it. So for example, 5 to the third means 5 times 5 times 5. Because there's 3. So 3 times. And 5 is called the base number. So that means that a to the 1 is just a because it's a multiplied by itself just one time. So anything to the 1 power is just itself. For that reason, for example, 5 to the 1 is 5. And then we get some slightly more complicated ones. So when you have a negative power, that means you divide it underneath 1. So a to the -1 means 1 over a, for example. So 5 to the -1 would mean 1 over 5. And then you can do more powers that are negative. So you could do a to the -n, and it means exactly what you think it means. So it means flip over a to the n. And so it means multiply a by itself that many times. So n times, but now in the denominator. So for example, 5 to the negative 3 would be 1 over 5 to the 3, or 1 over 5 times 5 times 5. So I guess 1 over 125 is what that would be. And then this sort of helps us figure out what a to the 0 is, which is the more trickiest one. So a to the 0, that's going to come from, actually first that comes after something else. So what about this? So what about a to the n over a to the m? So what if I have two powers of a divided by each other? What's going to happen there? Well, that's going to be a to the n minus m, whatever that number is. So it's easiest to see with an example. So for example, if I have 5 to the 7th over 5 squared, that means I'm multiplying 5 together 7 times on the top. 1, 2, 3, 4, 5, 6, 7. So there's 7 on top, and there's just 2 on bottom. So what's going to happen is, just like we saw with rational expressions, if you multiply things together, you can cancel the things that are divided by themselves. So 5 over 5 is 1, and then this 5 over 5 is also 1. So what you're left with is just 5 times 5 times 5 times 5 times 5, just these ones left. And the others divided by each other to become 1, and 1 times anything is just itself. So you just get this, and this is 5 to the 5. So notice that the 7 minus the 2, the shortcut is just subtracting the powers. So with that in mind, I can figure out what something to the 0 power is. So a to the 0 power I can think about as a to the n over a to the n, because that's a to the n minus n, which is 0. But what's anything divided by itself? That should just be 1. So this is why anything to the 0 power is just 1. So for example, 5 to the 0 is 1. Anything to the 0 is 1. Let's see, what other rules are there? A couple more. If I multiply two numbers together, so if I have two numbers instead of just a times b, and I do the power of that, well, that just means a times b times a times b times a times b, that n times. But then, because multiplication is commutative, I can switch the order. Everything's multiplied together. I can stick all the a's together. So it's just a n times. And then I could stick all the b's together. And that just means I get a to the n, b to the n. So the shortcut is that if you have multiplication, you can bring the power in to each term. So that's a nice little rule we have. Don't get this confused with addition. So this does not work for addition. So people often make this mistake. If you have a power outside of addition, you cannot just do this. So this would be extremely bad, very common error, but it does not work the same. For multiplication, it works. For addition, it does not work. Okay. And then one more rule is what happens if you take a power to another power? This one's a bit tricky. So this is saying I do a to the n times a to the n times a to the n. I do a bunch of these guys, m times. But that just means I have a times a times a n times, and then another one of these, and another one, m times, for a total of n times m a's. So the shortcut is you just multiply the powers. So you multiply n and m. So for example, 5 cubed to the 6th power is going to be 5 to the 3 times 6 power, which is 5 to the 18. For an example. Okay, so I think that's just about it for the basic ones. But the whole idea is that these rules also apply to variables. So we can use them to simplify some things. So for example, if you have 6x to the 4th over x cubed, there's this other idea of cancellation, slightly different than what we did before. So before we said like, oh, I have x minus 1 over x minus 1, so they divide to be 1. But here, we can use our new power rules. This is just 6 times x to the 4 minus 3. Because I have these having the same base, I can subtract the powers to simplify. And 4 minus 3 is 1. So I just have 1 power of x, which you just write as 6x. So we can use these rules to simplify expressions like this. Same idea if I had something like this, 6x minus 10 to the 4th over x minus 10 squared. I could do the same thing because these are the exact same base. I can simplify by subtracting the powers. So x minus 10 to the 4 minus 2 is 2. So I just got x minus 10 squared. Okay, and you can also do it with multiple variables. So for example, something like this, as long as everything is multiplied together, you can just add the powers up. And if it's on the denominator, you can just subtract the powers. So something like this, for example, because it's all multiplication, there's no addition, I could just multiply these together. I could bring the 3 to the 2 and multiply them together. I could multiply the x's together. I can multiply the y's together. Because it's all just multiplication. And then simplify from there by just adding powers. So when I have the same base, x and x squared become x cubed, because now there's 3 of them being multiplied together. Y squared and y cubed becomes y to the 5th, because 2 plus 3 is 5, and there's 5 of them total being multiplied together now. And then I get this. Oops, sorry, the bottom was a 5. Well, now the x's all completely cancel out because they have the same power. So 3 minus 3 is 0. So I'm left with x to the 0, which is just 1, which I don't have to write the 1. But the y's, 5 minus 10 is negative 5. So I'm left with the y to the negative 5. But now we can use our other rule. Y to the negative 5 just means 1 over y to the 5. So a negative power means flip it over. So then it simplifies to just that. Okay, so I want to do one last example that combines everything together. All the rules we have. So I'll use A, B, and C instead of X and Y, but the letters don't matter. Something like this. So first of all, because it's multiplication, everything is being multiplied together, I can bring this power to each term on the top and on the bottom. So it's going to be negative 7 to the negative 2, a squared to the negative 2, b cubed to the negative 2, and c to the negative 2, over 3 to the negative 2, a cubed to the negative 2, b to the 4th to the negative 2, c cubed to the negative 2. I could have also instead canceled before doing that, and we'll see that that's the same. But in any case, let's continue. So let's see, 2 times 2 is negative 4. So I multiply powers. If I have a power to another power, 3 times negative 2 is negative 6, and c to the negative 2. Negative 7 to the negative 2. I'll just leave it like that for now. And I'll do these: a to the negative 6, b to the negative 8, and c to the negative 6. So what I could do is I could do something like negative 4 minus 6 is negative 10. Sorry. Negative 4 minus negative 6 is negative 4 plus 6 is 2. So I could look at that and say that a to the negative 4 minus negative 6 is a squared. So I could just combine these to be a squared on the top. So I'm going to simplify different ones in different ways, but you could use any of these techniques that I'm using. So that the a's just become a squared. And that's fine. The other thing I could do is I could realize that, for example, b to the negative 6 means 1 over b to the 6th. So I could turn that into division by b to the 6th. And b to the negative 8 is 1 over b to the 8. But since it's already on the bottom, it's going to flip over. So 1 over b to the negative 8 is going to flip it over to the top. So that b to the negative 8, which is on the bottom, will actually flip to the top. That's one way to do it. And then I could cancel them. And I'll do the same thing here. So c to the 6th will go on top and c squared will go on the bottom. Okay, so now I could do 6 minus 2 is 4 to tell me that I have a c to the 4 left. B to the 8 minus 6 is 2, so I have b squared left. This a squared was already finished simplifying. And then lastly, I could use the negative power rule again. So negative 7 to the negative 2 means 1 over 7 squared. Sorry, negative 7 squared. And same thing with the 3. I could flip the 3 to the top and change the negative power to a positive power. So then finally, I just get 9 a squared b squared c to the 4th over 49. So negative 7 squared is 49. So that's one way to do it. There are many ways. I could have also instead simplified first. So let's just see that that's the same. So I could have just done negative 7 over 3. A squared over a cubed. 2 minus 3 is negative 1. So I get a to the negative 1. B cubed minus b to the 4th. B cubed over b to the 4th. 3 minus 4 is also negative 1. So that's b to the negative 1. And then c to the 1 over c cubed. 1 minus 3 is negative 2. C to the negative 2. And then I could bring in this negative 2 power later. So I could continue flipping these guys over. So negative 7 over 3. Now the a, b, and c flip over because of their negative powers. And now I could bring this guy in later to each term. And so now I get a to the negative 2, b to the negative 2, c to the negative 4, because you multiply 2 times negative 2. And then do the same flipping tricks as I did before. And I get the 49 on the bottom, the 9 on the top, the a squared on the top, the b squared on the top, and the c to the 4th. So you get the same answer either way. Math is consistent like that. Okay, so that's it for this video. See you next time.